Hi, and welcome to another Druid Summit 2022 session. This one is on SQL-based ingestion. My name is Sergio Farragut. I'm a senior developer advocate at Imply, and I'm joined by Karan.
Hi, this is Karan this side. I've been working in data teams for the last 10 years, contributing to various OSS projects like Falcon, Pig, Kafka, and Presto. For the past year, I've been actively working on core Druid development with Imply, focusing on the newly launched multi-stage query engine.
We're going to talk about SQL-based ingestion. We've separated it into two sections. One section talking about the new APIs and the SQL statements that it enables. And the second section where Karan will walk us through how it works. So the integration of the multi-stage query engine into Druid 24 enables a series of new features. First and foremost, it's this idea of batch ingestion using SQL, where you can do either appends or overwrites of data using insert and replace statements. And you no longer need to build JSON-based ingestion specs. This also comes with the new function, a new table function called extern, as part of the SQL dialect that enables the reading of external data at the query or at ingestion time. This allows us to do ELT kind of processing, right? Where we can load the data into Druid and then transform it in place by loading other data sources from existing tables or rewriting existing tables using just SQL. It enables a clustered by clause in SQL, which allows us to do secondary partitioning. This is multi-dimension range partitioning to get better distribution of segment sizes and better performance of queries by using filters on those dimensions. We'll talk about that in more detail. And finally, it enables aggregation at ingestion time using perfect rollup by specifying the group by in the select portion of the SQL. And we'll cover that too. So starting with the APIs, SQL-based ingestion enables a new endpoint where you can issue a post request to Druid v2 SQL task with a payload that includes two main properties: the query, this is the SQL that you're going to execute, and the context where you can specify execution parameters. One of the more important or more common parameters to use is MSQA num tasks. This allows you to specify how many workers are going to be involved in executing this particular operation. The response to this API is almost immediate. It will give you a task ID, which you can use to interact with the query with other APIs. In order to get the query payload using a get on the task ID, or to get the query status, the query report, which shows you the results of an ingestion or the retrieve results of a select statement. And finally, the ability to cancel the query using the shutdown API. So to the SQL, right? These are the three kinds of SQL, SQL-based ingestion or the multi-stage query engine enables. The first one is an insert into a target table. This allows you to append data to an existing data source, or to create a new data source if it doesn't exist, right? You specify the insert into the target table that you're adding to or creating, and then you specify a select, which drives the ingestion data itself, and we'll get into some more detail on that. You could also use a replace statement to replace a time interval within an existing data source using the overwrite where clause with a condition on the primary time column that specifies the time interval that you're replacing. In that case, the data that's being queried by the select needs to cover that same time interval. You can also use overwrite all if you want to replace the whole table. And just like in the insert, if the table doesn't exist, it will be created. Finally, the select statement allows you to test queries to external data before actually doing the ingestion. So as you're crafting your ingestion, you can test it using select statements directly on the external data. It's a good idea to limit those results so you don't calculate billions of rows and then throw them away instead of ingesting them. So you want to use limit to test your query, test the results of what you're ingesting, and once you're happy with it, do either a replace or an insert with that same select statement. So the other feature that we talked about is the extern table function. You specify it in the from clause as part of the select portion of the SQL. The extern function takes 3 parameters. One is the Druid input source. This is any of the Druid batch input sources that are supported traditional batch ingestion. You specify the input format just like you would in traditional ingestion, and all of the same data formats are supported. And finally, you specify the input row schema. This is a description of the fields that will be read off of the external files that are being specified in the first parameter. So one thing to talk about in Druid ingestion is how it organizes the data. So those of you that are newer to Druid will need to know that the data is organized in multiple forms when ingested into Druid. So you can have an arbitrary set of input files with data organized in any way. In this example, we have data that's timestamps across 4 different days, but they're not organized within the files. So Druid will first organize those rows by time and separate them into time intervals specified by the partition by clause. So in the partition by clause in SQL, you can specify second, minute, day, month, hour, any of the time granularities. And this will create the separate time intervals to organize the data in. In this case, we're doing partition by day, so we see a time interval for July 1st, a time interval for July 2nd, and so forth. And the rows that come from all of the input files are organized into those different time segments. Now, you could have one or more files within each of the time segments as a result of the ingestion. And you can control that by using the cluster by dimensions. So cluster by will take the data that has been organized into the time intervals and subdivide it further based on one or more dimensions that you specify in the cluster by clause. This helps query time because it helps increase parallelism by subdividing the data into more files, especially if you have larger volumes of data. You can process each of the files in a separate thread and therefore increase parallelism of the query and increase performance. It also provides better locality. And better locality means that because it's grouping similar values together, that provides better compression. So this reduces the resulting data size. By using this secondary partitioning strategy, it also enables better pruning. This is the ability to read less segment files at query time based on the organization of the data. And we'll look into that a little bit further. So the SQL statement, right? So this is an example insert or replace that, again, insert for appends, replace for overwrites into a target table, followed by the select. Now, the select needs to contain a few things. First of all, it needs to specify the time dimension, and that should be specified as __ time. This indicates to Druid that that is the primary time that's going to organize data on. And so you specify some SQL expression that takes the input field, in this case timestamp field, parses it into a timestamp data type. So it can be really any SQL expression that results in a timestamp data type based on the input fields. That's followed by dimensions and metrics that are expressed also as SQL expressions to process the data a little bit at ingestion time, do some transformations, or just to take the input fields directly and put them into the target data source. We've already talked about the from clause and the ability to specify external sources there. You can optionally specify a condition in the where clause to filter the input source and not ingest necessarily all the data. You can ingest a portion of it. And in both insert and replace, you will need to specify partition by clause. This is what defines the primary partitioning on time and how big those time intervals are. The cluster by is an optional portion of the SQL. So if you want to sub-partition the data within those time intervals, you can specify the clustered by, and you can use one or more dimensions in that clause. An important note here is that, at least as of Apache 24.0, cluster by will only work and it will only result in secondary range partitioning if a couple conditions are met. If all of the cluster by columns are string and they're single valued, you can't use multi-valued columns here, and you're using a replace statement. So it requires the overwrite logic in order to do the secondary partitioning. So how does this help at query time? We see here an example select from an ingested table where we're specifying some condition on the primary time column. This is a best practice. You should always specify some filtering on time so that Druid can do pruning on the time interval. And so this pruning is selecting a subset of the time intervals to read from instead of reading all of the time intervals. So in this case, it would only read the 2 segment files in July 2nd and the 2 segment files in July 3rd in order to process this query. Now, since we also clustered by dimension 1 in this case, if you specify as part of the where clause a condition on the cluster by dimension, that can be either equality or an inequality condition on that dimension, that will allow it to select a subset of the segment files within each time interval. So in this case, if we look at the condition where dimension 1 is less than or equal to b, because the segment files are split into ranges of the values of that dimension, we know that we only need to read the first of those 2 segment files in each of the time intervals in order to resolve this query. And that's how Druid will execute it. This is less processing, so less files to process means faster response times, and it also helps with higher concurrency. Another thing that Druid does at ingestion time is aggregate data. Typically when we're aggregating data in Druid, we specify something called query granularity. This is the ability to take the input timestamp, in this case called event time, and truncate it in some form, right? Truncate it to the minute, truncate it to the hour. In this case, we're truncating it to the day. In SQL-based ingestion, you can do it by using a floor or a ceiling function to truncate it to one of those granularities. And you target the underscore time column as the name of the target column, and that will specify time. So by truncating time and then aggregating on all of the rest of the dimensions, we can reduce the number of rows and calculate some metrics while we're doing that. In this case, we're doing the sum of the source metric as the target metric, and we've added a count here. You can do all sorts of different aggregations at ingestion this way. Let's look at the SQL. So again, in the SQL has the same basic structure. You need to specify the time column. Here's where you would do truncation of time. You can do any transformation on time that you want here, but typically you'll do a floor or ceiling on the time dimension such that you get that roll-up effect on time. Then you specify the list of dimensions from the input fields. If you have any multi-value columns, you'll need to surround them in MV2 array such that the values are kept as a single list of values and not unnested into individual values within the column. Then you specify the aggregate metrics. So the traditional ones, sum, min, max kind of aggregations, or one of the approximations that Druid supports can also be used here. When you're doing aggregation, you'll need to specify a group by. The group by must be on the time dimension and all of the dimensions that you have in your query. And you could also use partition by and cluster by the same way you would use in the non-aggregate version. Now, an important note here is that if you do have multi-value columns, you surround them with the MV2 array, but you'll also need to set the group by enable multi-value unnesting to false, such that when the group by operation executes, the multi-value strings are left as a list of values and not unnested into multiple rows, as would normally occur when you're running a select. Also, if you're using approximations, set the finalize aggregations to false in the query context. And what this will do is it'll store the internal state, so the theta sketch or the internal representation of that approximation algorithm in the segment files, which will enable further aggregation at query time instead of storing the result of that approximate calculation. Finally, SQL-based ingestion enables join operations at ingestion time. So you could have multiple external sources where one is, or some are sources of lookups, and one of them is a source of event data. You specify in the dimensions, like you would in SQL normally, the alias, in this case langs, which is the lookup for languages, to retrieve one of the other columns from that lookup. This is equivalent to what we would do in the transform spec lookup function in a more traditional ingestion spec. You also need to specify the joins, right? The first table in the from will be the event source. That will be treated in a distributed fashion, so each worker will get a portion of that external source, followed by joins of all the lookups. All the lookups will be broadcast to all workers. So one thing to consider here is that the lookups will need to fit in memory in every worker. So you don't want lookups that are too large, or you need to reserve the amount of memory necessary for the size of your lookups. Is really what you need to think about. So you specify the joins just like you would normally in SQL, and that's how lookups work in ingestion. So we've covered the APIs, we've covered the SQL functionality that multi-stage query engine enables, and now I'll hand it over to Karan to tell us how it works.
Thanks, Sergio. Now let's look at how SQL-based ingestion works internally. So the implementation of the multi-stage query framework uses the existing task-based model. We use the overload to spawn the containers. The request comes to the broker. We receive the request to the new SQL/task endpoint. The broker translates the SQL into a native query, which includes external data reference and a target table in case of an insert or a replace. MSQ uses an asynchronous execution model. So the broker forwards the request to the overload, which in turn instantiates a task and immediately returns the unique task ID. It is up to the calling application to check on the status and retrieve the results using the task ID. As we have discussed before, all the APIs for MSQ are async. On the overload, once the task is instantiated, it basically contacts this task is the query controller. It basically contacts the overload to spawn more workers based on the SQL query. After all the workers are launched, the query controller basically coordinates all the work amongst these launched query workers. This is something similar to an application master. In the multi-stage query processing framework, we have the query controllers and the query workers. The plan generated by the controller is coordinated among all the workers. The parallelism is controlled by a new context parameter, MSQ numTask. Query workers execute their portion of each stage in parallel and then shuffle the results of that stage in preparation for the next stage. Stages can do a lot of things in parallel, such as data source retrieval, aggregation, sorting, filtering, and even SQL-based transformations. When transition from one stage to another happens, the workers, if there is a repartition, they reorganize the result data in order to deliver the data in the format the next worker can read. You can see that each worker prepares the data for each of the target workers and then transfers the subset called partition to the corresponding worker. For sorting or segmentation with cluster by keys, we need a way to cut the entire dataset. We use item sketch for that. If the stage requires repartitioning, we first create the sketch in memory in the pre-shuffle phase. We downsample the sketch once it reaches a minimum of 300 MB or 10% of JVM. We send the sketch to the controller where it merges all the sketches. It might downsample if it hits the memory limit. Once all the sketches from all the workers are merged, we cut the sketch based on the number of rows, which is 5 million by default. The boundaries are set to each worker, and then the worker proceeds to partition the data based on worker boundaries. So the next stage can either be a segment generation stage in which we publish the segments to S3 or deep storage, or group by post shuffle phase, which is the merge phase in the external merge sort algorithm, which we will cover next. If we identify the query needs shuffling, we materialize the query into two stages, a pre-shuffle phase and a post-shuffle phase. In the pre-shuffle phase, we take the input data and start sorting it in memory, 37% of JVM by default. Once the memory fills up, we write out the file to disk. We also keep adding the sort keys in the data sketch, which we discussed previously. This keeps on happening until the entire dataset allocated to the stage worker is processed. We post the partition boundaries to the controller. We then start merging these files n way at a time in a level-based approach. Once all the files are merged, we wait for the controller to give us the partition boundaries, and then we start cutting the sorted data. After we split the data, the next post shuffle begins, which takes these M partitions at a time and then does a merge across multiple partitions of multiple workers. With this, Druid has now laid the foundation of shuffle joins. Like the smoosh format, which is used for deep storage segments, MSQ has a native format called frame format, which is used to transfer things over the wire. Two flavors are supported, row based and column based. The first version was columnar only, but we realized quickly that our primary use case is for sorting, hence row based format made more sense. In the row based format, it allows us to basically compare serialized keys. This helps in saving the deserialization cost and hence we become much faster. We are thinking of using the columnar format in the future for possibly scan queries. The goal for this format would be to use it across all broker historical communications in the future. One of the design goals for MSQ was that users should not spend a lot of time tuning memory. We have seen this problem in the classic native ingestion, where most of the users complain that Druid is hard to tune, and we also for ingestion, and we also agree. So, as part of that, initially in this new SQL-based ingestion, we took that as a design consideration. Hence, for that, we have split the heap and the we have split the memory into we have split the heap into two places. One is we first subtract all the lookups, all the data sketch sizes. Whatever is remaining, 37% of that we use it for in-memory sorting, and the other 37% for the processors like we are doing transformations, we are doing filtering. For that, 37% we are using of the heap we are using, and the remaining 25% we are allocating it for JVM other activities. As worker tasks use both JVM heap memory and off heap memory, it helps to improve performance in only certain cases. Some of them are when we are doing the segment generation, it becomes more efficient when the data does not need to spill each time. Secondly, while sorting data, as we have discussed before, the more memory we have, the less we spill to disk. This slide talks about how the local disk is used and what are the various stages we use it in. So we basically use it for three things. One is the segment generation. One is to basically sort the intermediate data, like we have discussed before. And third is to basically store the output of the stages so that the next stage can basically read that output. The frame format currently takes about, if we compare it side by side with the JSON, it's like 90% compressed. But we have seen in multiple POCs that people don't like to get bottlenecked on local disk. So for that, a lot of work is currently going on. We have a partial fix wherein the output data is used for the output data of the stage. You can now directly write it out to deep storage. So that does not bottleneck the disk. There is currently work going on, write out the intermediate data used for shuffling to deep storage. So that would be part of the 25.0 release. So we only effectively have one place, which is the segment generation phase, to where the disk is bottlenecked. But as we have discussed before, we have put a lot of work in coming up with the correct segment sizes. So if the segment sizes hold 5 million rows always, then we anticipate that we will never run out of local disk if we have all of these things enabled. Of course, there is a trade-off by using deep storage as the shuffle scratch directory, but that is something the users need to choose. Do they want a lot of elasticity or do they want speed? With that, we the future for MSQ is to basically have the worker fault tolerance, which will be part of the 25.0 release. We've already talked about how we'll be using deep storage as a cache directory for spilling intermediate outputs of the shuffling step. We also are There's a PR out which basically increases the accuracy of the sketches one time chunk at a time. So it would give us even better sketch boundaries. It will basically give us better partition boundaries, and we also plan to support streaming ingestion via SQL in the future. And yes, shuffle joins, as we discussed before, we have laid the foundations of shuffle joins, and it is being planned to be there in the future versions of SQL-based ingestion. With that, thank you.
I'll say thank you and remind you to star the repo, to go to learn.imply.io to get some free courses and certifications on using Druid. These are hands-on courses to take advantage of that. And finally, point you at the druidforum.org where the community members publish articles and do Q&A for each other and all participate there for the Apache Druid community. Thank you.